There is a motorcycle in existence that Harley-Davidson has never officially celebrated. It has no place in the company's marketing materials. It was never offered for sale in a showroom. And yet, it represents one of the most radical engineering decisions the company ever made. Somewhere between 1942 and 1943, deep inside a factory in Milwaukee, Wisconsin, Harley-Davidson built a machine that looked nothing like a Harley, sounded nothing like a Harley, and was powered by an engine that the company had never attempted before or since. It was called the XA. And the reason it exists is that somewhere in the burning sands of North Africa, an American soldier looked at a German motorcycle and realized that the enemy had built something better. Now, that realization set off a chain of events that reached all the way back to the steel mills of Pennsylvania, the aluminum smelters of the Pacific Northwest, and the machine shops of Milwaukee. It forced an entire engineering department to abandon 4 decades of institutional knowledge and start over. And it produced fewer than 1,000 machines, most of which have vanished from history. This is the story of how one motorcycle changed everything Harley-Davidson thought it knew about building engines, and why the machine that forced that change was born not in America, but in Nazi Germany. The year was 1942. The war in North Africa was raging. Allied forces under General Dwight Eisenhower had launched Operation Torch in November, landing troops along the coasts of Morocco and Algeria in an effort to squeeze Axis forces from the west, while British armies pushed from the east. The goal was to eliminate the threat posed by Field Marshal Erwin Rommel and his Afrika Korps and secure a path toward Italy. But the terrain was nothing like the European battlefields that most American planners had studied. North Africa was desert. Miles and miles of sand, gravel, and rock stretching to the horizon under a sun that could push air temperatures above 130 degrees Fahrenheit. Water was scarce. Dust was everywhere, and it got into everything. American reconnaissance units deployed to the theater quickly discovered that their standard-issue motorcycles were inadequate for these conditions. The Harley-Davidson WL and the Indian Scout were both 45 cubic-inch V-twin machines, so both chain-driven and both designed and tested primarily on paved roads in the temperate climate of the American Midwest. In the desert, the exposed chains that connected the engine to the rear wheel were exposed to sand that worked its way into the links and ground against the sprockets with relentless abrasion. Chains stretched, seized, and snapped. The air-cooled V-twin engines, while capable under normal conditions, struggled to dissipate heat in the brutal North African sun. Overheating was a constant problem. Breakdowns became routine. The Germans did not have this problem. Rommel's Afrika Korps was equipped with BMW R-75 motorcycles, and these machines were operating in a different class entirely. The R-75 used a horizontally opposed flat twin engine, also called a boxer engine, with its 2 cylinders mounted on opposite sides of the crankcase, pointing directly left and right, parallel to the ground. This layout was inherently smooth because the reciprocating forces of the 2 pistons canceled each other out. The R-75 was also shaft-driven, meaning the power was transmitted from the engine to the rear wheel through a sealed system of gears and a drive shaft, with no exposed chain or belt anywhere. Sand could not get into the drivetrain. The engine was wider and lower to the ground than a V-twin, giving it greater thermal mass and more surface area to shed heat. In the desert, the R-75 was not just good, it was dominant. Word of the BMW's superiority reached the United States Army's Quartermaster Corps, and the response was swift. The Army contacted Harley-Davidson directly. The company was already deep into wartime production, manufacturing WL series motorcycles and M8 armored cars for the military. But the Army needed something the WL could not provide. They needed a motorcycle that could match the BMW R-75 in desert conditions. And the fastest path to that goal was not to design a machine from scratch. It was to take a BMW R-75, disassemble it, study it, and build an American version. Harley-Davidson's engineers received the German machine, along with a set of specifications and a timeline that left almost no room for error. The project was designated XAX for experimental, A for Army, and the clock started ticking immediately. Before a single engine case could be poured or a single frame tube could be bent, the raw materials had to arrive at the Milwaukee plant. And in 1942, obtaining those materials was a battle in itself. Steel was the backbone of the XA. The frame, the suspension components, the gear housings, the exhaust system, all of it began as steel. America's steel production in 1942 was extraordinary by any historical standard. The mills along the Monongahela River in western Pennsylvania and the industrial corridors of Ohio were running around the clock. Furnaces burning day and night, rolling mills churning out sheet stock, plate, and structural sections at a rate that would have been unimaginable a decade earlier. But the demand was even more extraordinary. Tanks needed steel. Ships needed steel. Artillery shells needed steel. Aircraft carriers needed steel. A motorcycle program, no matter how strategically important, was a small consumer in a market dominated by the heaviest weapons of the war. Every pound of steel that went to the XA had to be approved by the War Production Board, the federal agency that controlled the allocation of industrial resources. Harley-Davidson's engineers had to justify their material requisitions against competing demands from every other branch of the military and every other defense contractor in the country. Aluminum was equally essential and even more contested. The XA's engine cases, the large castings that housed the crankshaft, the cylinder bores, and the transmission internals were made from aluminum alloy. Aluminum is lighter than iron by a factor of roughly 3, and it conducts heat away from hot components far more efficiently than steel. For an engine that had to operate in 130-degree desert air, aluminum was not a luxury. It was a necessity. But aluminum smelting is an enormously energy-intensive process. It requires massive quantities of electricity, generated primarily by hydroelectric dams in the Pacific Northwest. And the aircraft industry was consuming aluminum at a staggering rate. Boeing's B-17 Flying Fortress used thousands of pounds of aluminum in its airframe. Lockheed's P-38 Lightning was built largely from aluminum skin panels. Every aluminum ingot that Harley-Davidson purchased for the XA was an ingot that could not go to a fighter plane or a bomber. Securing the supply required negotiations at the highest levels of wartime industrial planning. Rubber presented perhaps the most acute crisis of all. The XA required 2 tires, but in 1942, rubber itself was a strategic commodity on the verge of running out. Japan's conquest of Malaysia, Indonesia, and the major rubber-producing regions of Southeast Asia in 1941 and 1942 had severed America's access to approximately 90% of the world's natural rubber supply. The United States had almost no domestic rubber production. Synthetic rubber programs, particularly the production of a material called GR-S, were being developed with enormous urgency. But in 1942, they were still producing only a fraction of what the country needed. Tires for military trucks, jeeps, tanks, and aircraft were all competing for the same shrinking pool of rubber. Every tire on every XA motorcycle was a direct cost measured against the tires on the vehicles that were carrying troops and supplies across oceans. The raw materials converged on Milwaukee by rail, the dominant mode of freight transportation in wartime America. Steel arrived in open-top gondola cars, each one carrying dozens of tons of billets, sheet stock, and formed sections. The railroads were operating under a kind of unofficial nationalization, with the Association of American Railroads coordinating schedules and priorities under government oversight. Military shipments took precedence at every junction, every yard, and every siding. A freight car carrying steel for a motorcycle factory in Milwaukee might sit for days at a sorting yard in Chicago, while trainloads of tanks and ammunition moved through on priority clearance. The journey from the mills of Pennsylvania to the plant on Juneau Avenue in Milwaukee was not long in miles, but in the congested, overstressed rail network of 1942, it could take far longer than peacetime schedules would suggest. Aluminum ingots traveled similar routes, so some arriving from smelters in Washington state, covering over 1,000 miles of track through a transportation system that was being asked to perform at a level it had never been designed to sustain. Once the materials arrived, primary processing began. Steel components that would bear heavy stress, crankshafts, connecting rods, gear blanks, were produced by hot forging. In the forge shop, steel billets were heated in gas-fired furnaces until they reached temperatures above 2,000 degrees Fahrenheit and glowed a bright orange yellow. Workers using tongs and automated handling equipment positioned the hot billets beneath massive hydraulic presses. Each press stroke shaped the steel, compressing it into the rough form of the final component. The noise was tremendous. Each press impact sent a concussive shockwave through the floor of the building. The heat radiating from the billets and the furnaces turned the forge shop into an environment that tested the endurance of even experienced metalworkers. Timing was critical. If a billet cooled too much between strikes, it became too hard to shape and risked cracking under the next blow. The foremen and the operators worked in a rhythm dictated entirely by the metal itself. Aluminum casting was a quieter but no less demanding operation. The engine cases were produced using sand casting. Skilled mold makers built patterns from wood or metal, then packed sand around them in a two-part mold box. The sand was mixed with a binding agent to hold its shape when the pattern was removed. Once the mold cavity was ready, a furnace melted aluminum ingots into a liquid state at approximately 1,300 degrees Fahrenheit. A ladle of molten aluminum was carried to the mold and poured through a channel called a sprue, filling the cavity from the bottom up to minimize turbulence and trapped air. The sand absorbed the heat. The aluminum cooled and solidified over the course of several hours. The mold was then broken apart, and the rough casting was pulled free. It was a crude shape, covered in sand particles and excess material along the seam lines where the two halves of the mold had met. But beneath that rough exterior was the fundamental form of an engine case, ready to be machined into precision. The factory floor was where the XA truly came to life, and where the full depth of Harley-Davidson's challenge became most apparent. The company had spent nearly 40 years perfecting the manufacture of V-twin engines. Every station on the production line, every fixture, every cutting tool, every assembly sequence had been refined over thousands of production cycles. The institutional knowledge of how to build a Harley engine was embedded in the skills of the workers, the geometry of the tooling, and the layout of the shop floor itself. Building a boxer engine meant dismantling much of that accumulated expertise and replacing it with processes that no one at the company had ever performed before. The aluminum engine cases, after arriving from the casting floor, were the first major components to enter the machining department. They were clamped into precision fixtures on horizontal boring machines, devices that held the casting rigidly in place while a rotating cutting tool removed material from the interior cavities. The cylinder bores were the most critical features on the entire casting. Each bore had to be perfectly round, perfectly concentric, and cut to a diameter that was accurate to within fractions of a thousandth of an inch. A bore that was even slightly out of round would cause the piston to rock inside the cylinder, leading to uneven wear on the piston skirts and the cylinder walls. In a military motorcycle that might operate thousands of miles from the nearest repair facility, that kind of premature wear could mean the difference between a machine that kept running and one that seized dead in the desert. After boring, each cylinder chamber was finished on a honing machine. Honing used abrasive stones mounted on a rotating and reciprocating mandrel to smooth the bore surface to a finish that was almost like polished glass. But the stones did not leave the bore perfectly smooth. They left a crosshatch pattern, a deliberate surface texture made up of fine diagonal lines running in opposite directions. This crosshatch served a critical purpose. It trapped small pockets of lubricating oil on the cylinder wall and prevented the piston from making direct metal-to-metal contact with the bore. Too much contact and the friction would generate heat, consume oil, and wear through the bore surface. The crosshatch was the invisible mechanism that kept the engine alive cycle after cycle after cycle. Getting it right required careful control of the honing speed, the pressure of the stones against the bore wall, and the length of each reciprocating stroke. Too aggressive, and the bore became oval. Too gentle, and the surface remained rough enough to accelerate wear. Each cylinder was measured after honing with a bore gauge, checked against the engineering specification, and if necessary, returned to the honing machine for another pass. There was no shortcut here. Each cylinder bore had to be correct. The crankshaft was forged from alloy steel and then machined on a lathe to bring its journal surfaces down to final dimensions. The journals were the cylindrical sections that rode inside the main bearings, and they had to be smooth, round, and precisely sized to maintain a thin film of oil between the shaft and the bearing. A crankshaft that vibrated even slightly out of balance at high RPM would transmit that vibration through the entire drivetrain and into the frame of the motorcycle. Over thousands of miles of operation, that vibration would fatigue the frame, loosen fasteners, and destroy the bearings from within. Balancing was performed on a dedicated machine that spun the crankshaft at operating speed and measured its rotational equilibrium using vibration sensors. If the shaft was off balance, a machinist removed material from the counterweights by grinding until the shaft spun with no detectable wobble. Every single crankshaft produced for the XA was balanced individually. There was no sampling, no statistical shortcut. Everyone had to be perfect. The shaft drive was one of the most significant technical departures from conventional Harley practice, and one of the most demanding systems to manufacture correctly. Instead of a chain running from a front sprocket on the engine to a rear sprocket on the wheel hub, the XA used a sealed assembly of bevel gears and a steel drive shaft. A bevel gear at the transmission output redirected the engine's longitudinal power into a lateral shaft that drove the rear wheel axle. The gears had to mesh with almost no play between the teeth. Too much clearance, and the gears would rattle, wear unevenly, and eventually fail. Too little, and they would bind under load, generating heat and stress that could crack a tooth. Cutting these gears required hobbing machines, which used a rotating cutting tool called a hob that moved in precise synchronization with the gear blank, gradually shaping the tooth profiles into the metal over multiple passes. After hobbing, the gears were case-hardened through a heat treatment process that created a hard outer surface while leaving the interior of the gear tough and resistant to shock. They were then ground on a gear grinding machine to achieve the final tooth profile and surface finish required for smooth, quiet, long-lived operation. Each completed gear was tested for fit against its mating gear before it was approved for assembly. The frame was fabricated from steel tubing, welded together by skilled workers using oxyacetylene torches. The geometry of the XA frame had to accommodate the wider boxer engine, that which extended further to either side than any V-twin Harley had ever used. This required a wider stance, repositioned foot pegs, and a fuel tank that sat higher to clear the protruding cylinder heads on both sides. Every weld joint on the frame was a structural critical point. A failed weld at high speed over rough terrain could send the rider into the ground at lethal velocity. Welds were inspected visually for surface defects, and where possible, radiographic techniques were used to reveal internal porosity or incomplete fusion that would not be visible from the outside. Final assembly brought every component together on a line that moved at a pace dictated by the complexity of the work, not by the speed of a conveyor belt. The engine was assembled first. The crankshaft was installed into the case. The cylinders were pressed on. With the pistons and connecting rods were fitted, and every bolt was torqued to the specification printed on the engineering drawing. The transmission and clutch assembly followed, then the shaft drive housing with its precision-cut bevel gears. The completed drivetrain unit was lowered into the welded frame, bolted in place and connected to the fuel tank, the exhaust pipes, the electrical system, and the foot and hand controls. Each finished XA went through a break-in run before it was considered complete. The engine was started cold and allowed to idle, then gradually brought up through its RPM range while a technician stood close and listened. A valve ticking out of rhythm, a gear whining under load, an exhaust leak hissing at a joint. Any of these sounds could indicate a component that would fail under operational stress. Engines that passed the auditory inspection were placed on dynamometers, machines that applied a controlled mechanical load to the output shaft while recording torque and speed across the entire RPM range. Each engine was run through a standardized test cycle to confirm that it produced the expected power output and that it operated smoothly without surging, hunting, or overheating. The finished motorcycles were painted in military olive drab, a flat, non-reflective coating that was standard across all American military equipment in every theater of the war. Reflective surfaces could betray a unit's position to enemy aircraft or observation posts, particularly in the flat, featureless terrain of the desert, where even small visual anomalies stood out against the landscape. The paint was applied by hand in a dedicated painting area, and each machine was allowed to fully cure before final components were installed. Completed Sebo motorcycles were crated for transport. Wooden shipping crates were constructed around each machine, padded with fiberboard to protect the painted surfaces and fragile components from damage during handling and shipping. The fuel and oil systems were drained completely to prevent leaks during transit. Desiccant packets were placed inside the crates to absorb moisture during ocean crossings. Each crate was stamped with requisition numbers and military destination codes, then loaded onto flatbed rail cars for transport to staging areas on the East Coast. From there, the machines were loaded onto cargo ships as part of larger military equipment shipments bound for overseas. The Harley-Davidson XA never achieved the widespread deployment it was designed for. By the time production reached meaningful volume and the first machines began arriving at military depots, the strategic situation in North Africa had shifted dramatically. Allied forces were advancing. Rommel was retreating. The urgent need for a desert-optimized reconnaissance motorcycle was fading as the war moved toward different terrain and different challenges. Production of the XA was halted after approximately 750 units had been completed. The contract was canceled. The specialized tooling was removed. The assembly line was reconfigured for other wartime production. But the XA left marks that outlasted its brief production run. The engineering lessons absorbed during the program, the experience of designing and manufacturing a boxer engine, a shaft drive, and a cooling system optimized for extreme heat, fed directly into Harley-Davidson's post-war product development. The company's K model, introduced in 1952, carried forward a number of the design philosophies that the XA had pioneered. The flat twin layout, the emphasis on balance and vibration reduction, the engineering philosophy of a motorcycle built for endurance rather than simply for speed. All of these ideas had their roots in the frantic months when Harley-Davidson was forced to build a German motorcycle in an American factory. Today, fewer than 100 XA motorcycles are known to survive in any condition. They appear at auctions for prices that reflect both their extreme rarity and their historical significance. For collectors, the XA is a tangible piece of the industrial war that ran parallel to the military war, a story of factories bending themselves to produce whatever the battlefield demanded. And for anyone who has ever studied how Harley-Davidson became the company it is today, the XA is impossible to ignore. It is the machine that proved the company could do something it had never done before. And it is the machine that proved, in the most direct way possible, that sometimes the greatest engineering challenges do not come from ambition. They come from the enemy.